We are looking at section 4.6 notes, example number 4. This is a new or special related rates type of problem where you'll have a container and then some fluid inside a container. If you were looking at an old version, it's possible that the rate of change that I have written here is different. Perhaps you have 10 gallons a minute. Please change that to 1.2 feet cubed per minute, as this example shows here. So follow along. A water tank has the shape of an inverted right circular cone of altitude 12 feet and base 6 feet. Water is being pumped into the tank at a rate of 1.2 feet cubed per minute. Approximate the rate at which the water level is rising when the water is 3 feet deep. To start the problem, let's get a picture of what this tank looks like. So here's the inverted right circular cone, like this. Okay, so that's the water tank itself. Now the water tank has a height of 12 feet. And I'm going to label the radius. So the radius is going to be half the base, or 3 feet. So that is the container. Now there's going to be a fluid inside the container, so I'm going to switch colors here. Now in this case the fluid is water. So the container has water in it, and the water takes on the shape of its container. So number 1, what is given in the problem? We're talking about the water, so we're going to continue to write this in the blue color. The volume of the water is increasing. It tells us that water is going in at a rate of 1.2 feet cubed per minute. So the rate of change of volume with time is going to be a positive 1.2 feet cubed per minute. Volume going in. That's the volume of the water. Next, we want to determine what we want to find in the problem. And in this case, we want to find the rate of change in the height of the water with respect to time, or dH/dt. And we want to find that when h is equal to 3 feet. Next, we need a relationship. Okay, we need to relate the V volume to the H, and we know that volume of a cone of this sort is going to be 1/3 pi r squared h. There's the relationship. Now we have a slight problem. If I went through now and found the derivative of this relationship, you would see that you're going to have a dV dt in it, you're going to have a dr dt in it, and you're going to have a dH dt in it. The problem with that is we have no information about dr dt, the rate at which the radius is changing. That's what makes this problem different. So, with that being said, we need to find r in terms of h so that we have the correct variables for the given information. So, what we need to do in this type of problem is come over, and I'm going to look at a cross section of the container with the water. So I'll grab the blue. See that? If you analyze this, you may see we have similar triangles where the height of the container is 12, that's fixed, and the the radius of the container is fixed at 3, but the water dimensions are not fixed. They will change as the water continues to come in. So we're going to say that the height of the water is h. That will change, and when it changes, it needs a variable name. And the radius of the water is r. So with these similar triangles, I'm going to set up a proportion. I'm going to say 12 is to 3, so the altitude of the container to the base of the container is equal to the altitude of the water to the radius of the water. If I cross the multiply, I have 12r equals 3h. And I'm going to solve for r, divided by 12, and so that's going to give me h over 4. So that brings us back to the relationship. And I like to say, like in Facebook, we're going to update our relationship status. Update. So now I'm going to write volume equals 1/3 pi. The radius now, instead of radius, I'm going to write it in terms of h. So h over 4 quantity squared. And then we have our trailing h. And I put a star here to show that I'm going to simplify this. I have a pi over, well, the 4 is going to be squared. That's 16 times the 3 is going to give us a 48. So pi over 48. H to the power h squared times h to the power of 3. So there's our relationship. After that, the process is going to be the same as the other examples, where we take the derivative. So I'm going to find the derivative of this relationship, dv dt with respect to time. Bring down the 3, so 3 over 48 is 1 over 16, so pi over 16 h to the power of 2 times dh dt, the chain rule. And there we have it. Now it's just a matter of some plug and chug. I'm not crazy about this decimal up here, so I'm going to say that 1.2 is actually 6/5. So I'm going to use that when I substitute. So at the snapshot in time, the rate of change of volume is 6/5. And I have pi over 16. My h at the snapshot of time is 3. Oh, that doesn't look like a 3. That's better. 3 squared. And dh dt is what we're trying to find, the rate at which the water level is rising. Beyond that, it's just simplifying or solving for dh dt. And that's going to come out to be 16 times 6 over 9 times 5 pi. So this goes in twice, this goes in 3 times, and that's going to give me 32 over 15 pi. And the units on that, the height is in feet, so feet, and the time is per minute. Moving on to example 5. Please pardon the crudeness of this example, as it was based on a childhood experience, Eagles versus Redskins football game. Anyway, we have a urinal that's 15 feet long and 4 feet across the top. Its ends are isosceles triangles with height 3 feet. P runs into the urinal at a rate of 2.5 feet cubed per minute. How fast is the pee rising when it is 2 feet deep? Pretty gross. Anyway, here is the troughed urinal. It has a triangle, isosceles triangle at the end, and then it goes out like this. Comes down like that. See the trough? I'm not sure how it's balancing, but there is the trough. So now, this is one of the types where you have a container and then a fluid in the container. So in this container is the fluid, P. Okay, see, that goes in there. Like the other problem, the container's dimensions are fixed. So let's write some of these dimensions down. The height of the urinal is 3 feet. The base of it along here is 4 feet, and then its depth as it goes back is 15 feet. And we're now going to look at the problem. So what is given? So like the other problem, P is coming in, so that's going to affect the volume. So dV dt equals 2.5 feet cubed a minute. That would be equal to 5 halves feet cubed per minute. Next, we want to determine what we want to find. And we want to find dt, the rate at which the height is changing. And we want to find that when the P is 2 feet deep. Ew. So now we want the relationship. So the relationship is going to be the volume of the P taking on the shape of the container. So we have a triangle times its depth, if you will. So the volume is going to be 1/2 the base times the height times the depth of this thing, which is 15. So let me just write that as 15 halves base times height. Alright, we're running into the same problem as the last. We would have a dv dt, and after the product rule we would have a db dt and a dh dt, but we do not have information on db dt. So we're going to have to set up a proportion. Change my color. Alright, so if I look at the cross section here, this is the container, which is 4 feet across by 3 feet high, and then we have the fluid, which is B as a base and H as a height. We have similar triangles again, so I can say 3 is to 4, that's the altitude is to base, as the altitude is to base. After cross multiplication, 3b equals 4h, and that leads us to b equals 4/3 of h. We're going to use that when we update our relationship. So we come over and we're ready to update. So our volume is equal to 15 halves the base, which is 4/3 h, times the height, which is h, and I'm going to star this because I want to simplify. Well, the 15 and the 3, that goes to 5, the 4 over 2 goes to 2, so that's going to be 10h squared. Easy enough. Okay, we are ready to go through our process, finding the derivative and then substitution. So let me come over here with this, and we have dv dt equals 20h times dh dt. We're ready to substitute values. 5 halves is the given dv dt. 20 at a snapshot in time. The height is 2, and it is at that time we want to find dh dt. So I'm going to simplify here. I'm going to divide both sides by 20 times 2. So that's going to be equal to 1/16 after I simplify, and that's going to be feet per minute. That is the end of example 5.